Hi, welcome to Lab 4. My name is Chelsea Thompson, and in this lab we are going to examine the motion of a mass oscillating on a spring. To do this, we made a model and compared this with the data gathered from the video and tracker. Here we define the system to be the Earth, the mass, and the spring. From this, we will use fundamental principles of physics, such as Newton's second law, the energy principle, and Hooke's law, to analyze the data and see if this model satisfies the energy principle that the change in energy of a system is equal to zero. Now we will focus on a few concepts necessary to do this lab. First, dealing with Newton's second law, we know that the only two forces acting on the mass are the force of the spring and the force of gravity due to Earth. Therefore, the sum of these forces are equal to F net. Next, dealing with the energy equation, we need to know that the kinetic energy of an object is equal to 1/2 m times the velocity squared. We also need to know that the potential energy of a spring is equal to 1/2 the spring stiffness times the stretch distance squared. And finally, that the potential gravitational energy is equal to mgh. Now let's analyze the tracker video. The origin is where the spring is fixed on the wall, and the calibration stick is set to 0.7 meters, which is the distance between the fixed point and the mass. To gather data from this video, I track the center of mass. The graph to the right shows the oscillations, and the data below shows the exact position the mass was at during a given instant in time. Saving this data as a CSV allowed us to use it in the GlowScript code to further model the energy principle. For the code, we first need to solve for the important values, as shown to us in the lecture videos. First, we define the period for oscillation, which is the time divided by the number of oscillations in that given period of time. Next, we solve for the spring stiffness, as well as the relaxed length of the spring. Now let's take a look at the GlowScript code to get a better idea of how these values play into the model. First, we input the given initial values into the model. Here, the ball mass is equal to 0.402 kilograms, and the initial position was found from tracker, and the initial velocity is 0, as well as the time. Next, we input the values we previously calculated. Here we know that the spring constant is 6.83, and the relaxed length of the spring, as we will call L naught, is 0.123, and that the total length of the spring is equal to the ball position minus the fixed point of the spring. Next, a while loop is used to calculate the net force in the system. Here, Hooke's law is used to find the force that the spring has on the mass. Then, that force is added to the force of gravity to get the total net force. Next, kinetic and potential energy values for the system are found using the formulas that were previously identified at the start of the video. This loop tracks the changes in energy throughout the video, and as you can see in the results, the change in kinetic and potential energy are both oscillating, and the sum of the two is always equal to 0, which is the yellow line shown on the graph. This graph shows that the model satisfies the energy principle because the sum of the changes in energy are always equal to 0. To answer part 2 of the what does it mean question, I calculated the period for both the x and y components using the formulas you see here. As you can see, the periods are different. This can be attributed to the x period being more related to the pendulum motion the spring has while it appears to be moving in a circle, and the y period is more related to the oscillating motion of a spring only in the positive or negative y direction. This is why these values are different.